Awesome, right? All right, so we're going to talk about one last condition with the simultaneous linear equations and solving them that I want you guys to be aware of and keep an eye out for. It has to do with something called conditioning and checking to see if your solution is ill-conditioned or not. Your system of equations is ill-conditioned. Typically, this condition occurs when your equations may be constructed or based upon experimental data. And so this is actually something you can see in the engineering context. If you've been doing a bunch of data collection and data analysis, you could end up with this kind of situation. So I'm not going to write the equations out. I'm just going to write the coefficients out here. You can reconstruct it. So we have 4 variables and 4 equations. So that part is consistent. So you got 10, 7, 8, 7, oops, and then 8, 6, and 9, 8, 6, and 9, 7, 5. All right, so let's just double check that. 10, 7, 8, 7, 8, 6, 10, 9, 8, 6, 10, 9, 7, 5, 9, 10. Does that sound right? Yep. Good. And then the right hand side, 32, 33, 33. Okay, so I want to solve this, right? So I basically have 4 unknowns. I can think of them as X, Y, Z, and W, or whatever letters you want, A, B, C, D, doesn't matter. I'm going to solve it. So, oops, what did I do wrong? That was not supposed to happen. All right, let's do the numbers again. I'm going to read them off. Somebody check. 10, 7, 8, 7. Yeah. 7, 5, 6, 5. Oh, that was my problem. I duplicated that row. Sorry. Okay.
7, 5, 6, 5 or 7, 5, 6, 7?
7, 5, 6, 5. 8, 6, 10, 9.
Yep.
Yeah. 7, 5, 9, 10. Yep. There you go. All right. Woo. That was not what I was expecting either. No. Oh, he's wrong too. Mother. Sorry.
You're doing it in the dark over there.
I know. Well, there you go. Yeah, that's what I was expecting. Okay. So our solution comes out as all of our unknowns being equal to 1. Okay? And what happens in an ill-conditioned situation is if you just make subtle changes to your V vector, you get very big changes on your results. So let's try that. Let's just go here. And it's really, it doesn't take much. Really small changes in the B. And I get some pretty big changes in my results. And what this tells you is that you probably have an equation that is extremely sensitive, and your results need to be taken in sort of like in that consideration of the sensitivity. So maybe your conclusions are not very strong if you've got this sensitivity. Now MATLAB has a really nice function called rcond, R-C-O-N-D, to check this. And I forget how to use it. Okay. So if the result of R in rcond, which is the conditioning variable, if that value is close to 0, then you may be ill-conditioned. If that value is closer to 1, then you're okay. So we could go back a couple of examples to, let's say this guy, that equation, we didn't really have any problems with. Let's check archon on that. And we see that we're much closer to 1. So we're not so bad. Gives us a sense of the sensitivity of our solution to changing numbers. So that is, oh, sorry, go ahead. Yeah.
When you say sensitivity, what do you mean?
Sensitivity is this concept of if I draw some sort of engineering conclusion from some observations, and I say, okay, this is the way it is, okay? I should always ask the question, how sensitive is my conclusion to some changes over here? If a very small change over here makes this conclusion completely wrong, then I'm very sensitive. That would be my sensitivity analysis. I'm very sensitive to small changes over there. If, on the other hand, I can make lots of big changes over here, and my result still comes out the way it is, then my sensitivity analysis says my result's pretty strong, robust, there's no sensitivity to that.
So this is what you want us to use variables in our script.
No, that would be different. That's more of like making your script flexible for you to continue leveraging in the future. This is more or less like, okay, let's take an example of let's take materials. Yeah. Describe me an experiment you do with materials. Anyway, pick a simple one. Why are you laughing?
Smash their concrete.
Making a smash. So, what pressure are you typically breaking stuff?
Like 3,000 pounds.
How much?
5,000 pounds.
5,000 pounds. Okay. So you could ask your question. You could ask your question. You know, if I change the moisture content of my concrete sample, how sensitive is my end result of pressure that I need to break that concrete? Okay.
Some are breaking like 5,000.
Right. So like. Okay. So there's a significant amount of sensitivity in the result of what pressure does it take to break the concrete, and what is it sensitive to? Like, what are the input factors?
How much sand, grout that you got in there?
Okay. So all of those variables, all of those input factors have a high degree of sensitivity towards the pressure you need. Or another way to think about it, the pressure you need to break this concrete is highly sensitive to those input factors. Okay? You could envision an alternative universe where those factors have zero influence, and the concrete always breaks only at 5,000, period. And so you would do a sensitivity analysis, which is what you effectively can do in materials. You have 5, 10, 15 groups that have different concrete. If all of them break at only 5,000, then your conclusion is, you know, I have confidence that 5,000 psi is not sensitive to those input factors. You may not be looking at the right input factors. Maybe other factors are. You're in the engineering business, and you want to make concrete that always sells at the breaking, what's tensile strength? What's that term?
Mm-hmm.
Compression is 5,000 psi, and suddenly sand gets really expensive, and your boss is like, dude, just put gravel in there. Before you say, okay, do a sensitivity analysis. If the result says, hey, my concrete's fine if I swap all the sand for gravel, you know, that's an example of an engineer, a materials engineer, or civil at this point, doing a sensitivity analysis to see if they can make, you know, an economic decision with engineering judgment. It just got out of it. It wasn't like I was giving a secret.
So what's the range again? Like of sensitivity? What's my?
So close to 0 is ill conditioned, and closer to 1 is well conditioned. So this set of equations has some sensitivity, but not. Okay. That other one is a little bit further down. Yeah, negative.
Yeah. So what is it the computer's doing when you type in that command?
Archon, I don't know the big guts of Archon.
But you put in your matrix,
Yeah,
into Archon.
yeah. Cool. Yeah, that's what yeah, yeah, sorry.
So our content one is perfectly insensitive.
Effectively, you could say that, yeah. Which would be odd, right? Like,
Yeah.
okay. So let's look at an example where we can use the matrix math to our advantage. To do something interesting. Yeah? The book gives us two examples. One is called the Leslie matrix. There's a homework for the Leslie matrix, which I've started putting together, but it's kind of not completely done, so I'll have that done by tomorrow. I'll give you a sense of what that's saying. And the other one is a Markov process. You may have, these terms may sound familiar to you at some point. But yeah. So Leslie matrices are handy in looking at either you might think of it as looking at cohorts and how cohorts grow or go through a process, or how populations can grow or go through a process. Where could this be applicable? This could be applicable in manufacturing processes, and I'll give you an the homework is more of an academic study. I hope it's sort of. So the example we're going to do now is one of population growth. Okay, and you can pick any critter you like. Anybody has a favorite critter you use? Rodent.
Yeah, we're talking about what we did. So those skunks and yellow.
Skunks? You have a favorite?
Yeah, we're talking about drowning skunk. I don't know.
Something cute.
It was a good trick.
Komodo dragon.
Yeah.
Dragons. Okay, dragons. We're going to do Leslie matrix on Komodo dragon, which is not a real dragon. There's no such thing as a real dragon. Aren't Komodo dragons like almost extinct? So they like only have some islands.
Well, they just like made it so people can't travel to the island.
Yeah,
so people were stealing them from the islands.
Okay. Cool. Okay, good. Okay, so we're going to keep this problem relatively simple, and then the homework gets a little bit more complex. But let's say we have dragons, and we're going to put our dragons into 3 bins of age groups or cohorts. Is the way to think about this, okay? We'll call them the young, the middle, and the old. Okay? So at any given moment, there's a certain number of dragons that are young, a certain number of dragons that are middle, a certain number of dragons. Okay? We are going to represent that by x sub I. This is the population. So I'm going to keep some of this generic here so you can start applying it to other circumstances. But the example here is clear that I've got young, middle, and old. There are 3 bins. The bin refers to this group or this group. In a college setting, you can think of freshman, sophomore, junior, senior. Those could be your bins, right? It could be a manufacturing process. The first part is like melt the material. The second part is do something else, right? So the bins, by definition, don't have to be age group. It can be whatever bins, but you have a process and a flow that moves forward. Everybody okay with that? Yeah. All right. So then you have this notion of a survival factor. That's the technical term from sort of population dynamics. We're going to think about it as more or less, we'll call it a graduation rate, okay? And the way we are going to think about it is, what is the rate of these dragons that move from young to middle, and then middle to old, and then from old out to Never Never Land. Okay? That's what we mean by graduation. Okay? And we're going to refer to that as P sub I. Everybody okay with that? Okay. So then, not all of your Leslie matrices are going to have something like this, but then we have this notion of fertility rate, right? So our dragons are going to give birth to little dragons. Okay. And the question is, for each bin, what is the fertility rate, or how many dragons are they going to give birth? And that's kind of how you see new things as you go through your sort of population exercise, your population simulation. Everybody okay with that? Those three concepts? This first one, how many you actually have in a bin. The second one is what fraction of that is moving forward, so graduating into the next bin. And the last one is how prolific these dragons are. Okay with that? Okay. So I hinted that we are going to do a bit of a simulation type thing. We're going to use matrices here to do a simulation. Okay. And like we've sort of seen the simulation thing a little bit. What is something that you might see anticipate coming if you've got a simulation? You've got the progression of think of the steps for iterations, and if it's a simulation, it's typically the progression of time. So we are going to effectively have like a t+1 and a t. Right? T is the current time step. T+1 is the next time step. Right? And all of the stuff in t is going to influence t+1, and then we just repeat again. Right? We advance t, we do it again. So what we're going to do is effectively using these factors up here, and we'll put some numbers to this in a moment. We're going to come up with equations for how this process or population sort of increments through time. Okay. All right. So let's say that x to x1 of t+1. Okay. That's this bit, right? That's the youngest. So if you just think through this scenario that I've described. Given these factors that are here, what do you think influences the population that's in this group? Say again?
Field.
Say again?
Field.
How does field influence this?
Fertility.
The fertility rate. Okay, great. So in a way, we could say that. Well, okay. I can ask you guys a question. Are the young fertile? Typically no, right? So yeah. So let's just say that there's no fertility here. Okay. And I think in any of these problems, you have to think through all those scenarios, right? The manufacturing process or some other thing, you have to think through the scenarios. What's happening, right? So let's just say there's no fertility in that first stage. So what does this look like algebraically based on those variables that I have up there?
So it'd be like P, I.
Okay, so let's put a number to I.
Oh, P1 times F1.
So P1 would correspond to this guy. And we're saying there's no fertility here. So we can skip it.
Oh, yeah.
But if our young were having a fertility rate, then you'd be right. So let's start with P2. What do we multiply P2 by? So that's a rate, so we're going to multiply it by some.
P is the graduation factor.
Oh, sorry. Yeah, thank you. So the fertility rate tells you the number of baby dragons per grown-up dragon. So what should I multiply this by? Yeah, in that bin, right? So the number of middle-aged dragons I've got multiplied by the fertility rate is part of what's going to be in the bin. Yeah. Okay. Good. And then
Well, are we gonna say there's a fertility rate in the old?
Yeah, let's go ahead and do that.
So
Okay.
that would be plus though, right?
Plus. Great. Okay. And each of these, just to be super clear, is from the current time step. Whereas that's 2 plus 1. Yeah. Everybody okay with that so far? So what's the equation look like then for x2?
Subtract the graduation rate.
You know, I was just thinking that myself. I'm trying to figure out why I don't have that.
You know, what happens when you graduate from old?
Beyond. Graduate this semester.
I'm actually questioning the way he's got this set up now.
It's not to have a subtraction of the.
This is Hans' problem.
Yeah, it sounds problem.
Now it's our problem.
Yeah, now it's our problem.
We should send him an email. See how he responds.
If it's a graduation rate, it wouldn't really just be like, you wouldn't just subtract. Yeah, you'd have to like.
I don't like
develop-
this. I don't like this primary.
You'd have to develop the population size of that given period.
Yeah.
And then multiply it by that graduation rate and then subtract that.
That's a new problem.
You know, irrelevant of how he does it, we can do it how we think we should do it. So we can do it that way, right? So, yeah, I totally agree. So let's take, what are we going to subtract out of this population?
P.
P1, right? Because that's who's graduating, times F1, X1.
Yeah.
Right? So it's saying the current population times the graduation rate comes out of this group.
Are you saying X2 of T there and X3 of T?
Yeah. Yeah. And I'm going to adjust this a little bit so it helps us do our matrix creation. Yeah, I'm okay with that. Let's do it. We'll get a different result than Han, but it's okay. Because I like this grading better anyways. This is X. Okay, good. Let's do X2. So now we're concerned about this one here, right? What does our population look like for the middle? Do we have any birth into middle age?
No.
No, no birth into middle age, okay? So who's coming into middle age? Times which one?
One.
P1. Very good. Do we have any dependency on the other guys? Yeah, we have a graduation rate.
Minus P2X2.
Okay. What are we doing? Plus P2, minus P2?
Minus
Okay. Okay.
So it's not minus 2?
that was already.
Isn't that equation saying that all of the young is going to graduate though? They all graduate. This is the okay. This is a fraction of the young, P1.
Oh, okay.
So it's saying some fraction of the young at every time step, some fraction of the young become middle-aged. Yeah. This is trying to say some fraction of the middle-aged become old. What we're missing here
Is the initial population.
no that initial. You mean X? Like what happens at X1?
No, like
P2.
Well, whatever was in X2.
whatever was the next two originally.
Yeah.
Like you have to import an initial population for these to affect that number.
Right. And so that is effectively you could say plus X2 of T, right? It's your current population of X2, right? Minus the people leaving, plus the people coming in. You okay with that?
Yeah.
What's that?
I think we had it.
Initial children.
No, we don't have it. Yeah. Yeah. Okay. Good. So what's the next one look like?
P2.
So we're on X3. Does X3 have any influence from X1? No. So we could think of that as 0 here. Okay.
P2X.
So what happens? We plus P2? Okay.
Minus P3X.
Yeah. Okay, good. We okay with that? Pretty happy with it? Let's rewrite these a little bit so they're ready to make our Leslie matrix. Okay. We basically have 3 unknowns. Effectively, the one way to think about is X1, X2, X3 are your 3 unknowns. And what I want to do is get to a place where we have coefficients for each of those that are just nice, clear, right? So let's do X1, T plus 1 equals 1 minus P1, right? Is that correct? You okay with that? What's this one look like? Why is it 1 minus P1?
Because we have the initial pop text.
Oh, I didn't see it. Sorry, it's a little small. Do we have any dependency on X3 here? Okay, last one.
Zero.
0. And a very similar thing, right? Oh, okay. You okay with that? So what we want to define now is this Leslie matrix, which is basically just the coefficients out of all of these. Okay?
What's that plus a zero referring to?
Sorry, which one?
We got multiple plus a zero.
Just look at the location with variable. Yeah, like that's where X3 would.
This is this one?
That's
Or this,
where
sorry, this one, yeah. This is a placeholder to kind of give me my 3x3 rectangle,
Oh, I see.
right? Like this is, I'm saying here explicitly that there's a zero coefficient for x3.
Oh.
Here I'm saying explicitly there's a zero coefficient for x1. And the reason I'm being explicit about that is because in my Leslie matrix, I got my 0, 0, 0.
Leslie?
That's what it's named after. Yeah.
Well, there's a person named Leslie.
Yep. Okay, so given that Leslie matrix that we have up there, and we kept this generic without plugging any numbers in, because now you can experiment with different values for your quote unquote your graduation rates, etc. So let's just put in the numbers the book uses for starters, and we can play with it a little bit, right? So they assume the fertility rate of 0 for F1, which is what we did as well. F2's is 9, F3 is 12, okay? And then P1, P2, we didn't have a P3, right? Did we use a P3? We did. They went 1/3 P1. They went 1/2 for P2, and they don't use a P3. They assume 1. They basically say that once you're old, you die the next time step. That was
Whoa.
yeah.
Brutal, man.
Yeah.
You need to write up a letter.
That was Hans' conclusion. So I know this seemed like a long struggle to get to this spot, right? But the cool thing here is I'll show you a way that you can effectively do a very fast simulation with a few lines of code in MATLAB that allows you to simulate this process. Oh, geez. All right, let's get this on so it's not so dark. What's that?
God,
We're graduating.
It's the next step.
Sorry about that.
That's good.
Is that better?
Much better.
That's pretty good.
I'm going to put it to here so I can actually read that. Edit. Even though I put that. What's that?
I want to buy you a headlamp.
Okay, wait, so I blind you guys every time I turn around. Freaking actually hate that part about headlamps. Blinding anybody? Blind everybody. Okay. Oops. Ah. It really would help to have a light over here. There, we're gonna do that. There we go. Okay. Can somebody read off to me what we have there generically?
1 minus P1,
Okay, hold on.
L equal. And then we have F2. We have F3, and semicolon. Then we have P1, 1 minus P2. Then we have a 0. Semicolon, and then 0. P2, 1 minus P3.
Awesome. Thank you. All right. Why did I do it that way, guys?
You need a matrix?
I'm creating a matrix. Why did I put numbers in there?
You could sub it out really easily.
Super easy, right? So now up here, I'm actually going to make this a little bit different. Yeah.
Is that legal?
Is it not?
Oh, you're gonna index it.
Okay, and what did we decide my P looks like? It's 1/3, 1/2, and 1, right? And F is 0, 9, 12, right? So this might seem like Greek. It's MATLAB. Well, you know, this is me trying to like minimize how much work I gotta do. If my numbers change later, this is my way to minimize my effort later, right? This Leslie matrix consisting of all variables. The way I've defined this problem, that should not change, right? I mean, unless this dragons start behaving differently, like somehow young dragons start making kids. Unless that kind of thing happens, this is fine, right? This is unchanged. Now, what could change? Because of the various conditions, you know, like maybe there's humans are killing them, so the fertility rate's not as good, or something like that, right? So those numbers can change, and those numbers I can easily change by just going up here. I could have created separate variables, P1, P2, P3, but why do that? I mean, I've already got that 1, 2, 3 concept of indexes. I can make a vector instead, and super easy, I can just index into a vector instead. Yeah? So let's convince ourselves that this works. Does that look about right?
We're missing about it.
You are missing a value. Did I?
But maybe no, it's because it's 1 minus P and P is 1, P3 is 1, so it's
Oh, that's right. 1 minus 1 is 0. You guys see how that worked? All right, good, awesome. So I'm almost done with my my problem. That's the cool part of this. So I want to do, let's say this is month by month. I want to do 24 months. I'm going to do some iteration here. Anybody want to give me a suggestion for how I should do it? For loop, awesome. For loop. Okay, for time equals 1 to 24. All right. Maybe I want to take a guess as to what my equations might look like. I'll give you a clue. It's equals L, my Leslie matrix, which is my coefficients. This is almost the same. This is the same math as doing the residual calculation, right?
doing the residual, so it would be star. But what do we multiply it by?
So remember, once I go to MATLAB land, I lose my t+1, t-1. I mean, depending on how I build this, right? I can either have 1x that represents my population. Oh, wait. Yeah, x represents x1, right? x1, x2, x3 represent how many are in each of those bits, right? So that's what I'm going to use here. x1, 2, and 3 are going to represent the number of population in those bits. I'm going to take that and multiply it by my Leslie matrix, and that's going to give me the solution for the next time step. So the only thing I'm missing here is maybe a display statement so I can see what's happening. Let's do that just for fun. My end. And the only thing I'm missing here, can anyone help me with what I might be missing?
You need X to be defined.
I need initial condition. Yeah, so the question is really, what is my initial population? What is as the simulation starts, what are the initial populations in the young, middle, and high?
Well, the way it's set up, you're only defining one initial population.
I think the way you guys set up, you can have an initial population, all the bits.
Yeah. Oh, yeah, because you could, yeah. I keep forgetting vectors.
All right, so let's say we have 10, 5, and 1. All right. Should we try it out?
So should change the T to like I.
Oops. Yeah. Thank you. Oh, what did I do wrong? Oh, okay, you guys can help me out. What did I do wrong? Super simple mistake that I guarantee you all of us will make again. I'm multiplying L by X.
And columns here for the transpose. You needed
What do I need to transpose?
The X.
The X, right? Because my math here, my math is this. The number of rows of L, sorry, the number of columns of L must match the number of rows of X. Where should I do the transpose?
Oh, at the top.
Everybody okay with that? All right, let's try it again. Oh boy. There we go. So our numbers get pretty big here fast. Sorry. Anybody know the best format to use off the top of their head?
When was the last one you tried?
Long? Well, you don't want decimals, right? Because the population.
That sort of works.
Change round it.
Yeah, you can round. Or what is the one that rounds down? What?
Okay, cool. So what we can see here is basically simulation time steps and the progression of that population as we go forward. Okay. The way the for loop is set up right now, one is actually after one simulation time step, so it's not actually that initial condition. We can change that around a little bit in the for loop if we wanted to. Yeah. So this mostly was not to really talk about population dynamics, but this was to talk about using this Leslie matrix as a way to progress through a simulation. And very quickly, like the code is very compact. It took a while to think about how it would work, but the code is extremely compact. And this is one example of sort of the power of using a matrix to do that. Any questions on, let's see, this very simple code versus sort of the problem statement and how we got here? Yeah.
So what role do those parentheses play here?
Which parentheses?
In the Leslie vector.
Here, these are the indexes to those vectors.
Okay.
P, F, and X are vectors, right?
Yeah.
P1 refers to the index 1 of P. F1 refers to index 1 of F. How are we doing on that? Do you guys want to do the random walk or go into functions? What kind of question is that?
Walk?
Yeah. This Markov process is called a random walk.
Yeah. Let's do
Yeah. Similar to this, but a little different.
it.
I do it?
Yeah.
Are we going to need to come up with that equation that you put in the L matrix?
Yes. For a homework. So This is okay. So the homework's not fully framed out, but here's. I'll give you the homework.
Are we back with Elon or what?
We are.
Elon, yeah.
Elon decided to start an academy. Elon Academy. There are 5 tiers in Elon Academy. It's very difficult to move from one tier to the next. Not only must you be knighted by Monty Python, you must also be knighted by Elon Tusk himself.
Does he ever show up to campus?
I mean, he doesn't have to be there every time for that. There's a limiting reagent. Didn't think of that.
And so there's an initial population in the academy. Every tier, one of the requirements in your participation in Elon Academy is you must recruit newcomers, and there is a formulation on how the recruitment process works.
Oh, it's a pyramid scheme.
It is.
That's great. Oh, be on. We should have been suspicious of that.
So I'm trying to emulate this example here, but I said. And this plus the Markov process is one I will scan. I won't be able to do that until tomorrow, but I will. Okay, let's do the Markov process, shall we?
Yeah.
Okay. So this is less a simulation and more an assessment of probabilities. And how, after playing through a bunch of iterations of the computation, where the probability lands. So this the random walk comes from the example that's often given, which is a walking example. If you imagine a student who on one side has their home, and on the other side has a cafe. Actually, let's make it more interesting. Bar. And there are. Are these still dragons? No, these are people.
We should probably erase that.
Oh, yeah. Student. If you imagine there are many intersections in between. Is it still on the. It's really dark on that side. How many have I got? Oh, perfect. And the exercise for the random walk basically goes like this. At any one of these intersections, there's a 1/3 likelihood the student's going to go home, and a 2/3 likelihood the student's going to go to the bar. Right? So if the student is here, going that way, 1/3 likelihood, going that way is 2/3 likelihood. Okay? If they end up here, they're going to stay there. And if they end up here, they're going to stay there. Okay? And so the question is, this is the random walk, right? Given a student starts at a location, what's the likelihood they're going to end up either over there or over there? So you can effectively run through this kind of with the probabilities and figure out where the student's going to end up using the Leslie matrix. Yeah? All right. So let's frame this up a little bit. So the first step is to actually develop this matrix, right?
Just one question here. It's the only intersection variables that we're dealing with are either towards home or towards bar, right?
And we're actually going to represent it as one matrix through the Leslie matrix. And it represents, depending on where you are in the matrix, what's the likelihood that you'll go one way or the other. So So the way this is intended to work is that, oops, sorry. Okay, so yeah, the column current. Sorry. So the thinking here is that if you are at this spot, what's the likelihood that you'll go home? Okay? So if you're at the bar, likelihood that you're going to go home in the next step is 0. If you're at 5, also 0, right? So this is all zeros until you get to here. If you're at 2, what's the likelihood you'll go home?
1/3, 2/3.
Oh, that's how we're framing it.
Oh, okay, okay.
Because we all have a preference for the bar.
Fair enough.
And if you're at home, you're staying home, right? So this is the 1. Okay? All right, let's do the next row. You're at the bar. What's the likelihood you'll end up at step 2? 0. Okay. Where's the first step where it's not 0? And what's the value here? If you're at 2, we don't permit that, right? We're basically, this is a random walk. So this is, again, the framing of the problem. You could frame it differently. So this is going to be, if you're at 2, what's the likelihood you'll stay at 2? If you're at 2, 0, right? Because we're saying at every intersection, 1/3 likelihood that you'll go home, 2/3 likelihood that you'll go to the bar. So this is 0. What if you're at home? What's the likelihood you go to 2?
Oh, I see. Okay.
Oh, no, 2/3.
It's
You're
0?
staying home.
Oh, you're staying home. Okay, okay, okay.
Okay.
I got the logic now.
Next one.
0, 0.
Yeah, I got a 2 there.
So if you're at 4, what's the likelihood you go to 3/3? 1/3. If you're at 3, what's the likelihood you go to 3?
0.
If you're at 2, what's the likelihood you go to 3?
2/3.
If you're at home, what's the likelihood you go to 3? Okay, great. We can fill the rest of this in, right? Oops. Oops. This is a special value also, right? You're at the bar, what's the likelihood you're going to stay at the bar? Wait, I got offset here somewhere, didn't I? I skipped the line. That's the line. Sorry. Right, because this is 4, 3, 2, this is 4. Sorry. Let's fix that. Right, if you're at the bar, the likelihood you're going to go to 5 is 0, right? If you're at 5, the likelihood you're going to go to 5 is 0. If you're at 5, yeah. If you're at 4, the likelihood you're going to go to 5 is 2/3, right? Okay. My rows got misaligned, and that's why it's a little bit. There we go. So if you're at 5, the likelihood you go to the bar is 2/3. If you're at the bar, the likelihood you stay at the bar is. Is everyone okay with the framing?
So we're assuming that if you're either at the bar or at home, you're not going anywhere.
That's right.
Okay.
And those assumptions could change, right? In a different problem, come up with a different answer. Different framing, different answer.
So what is the basis of this problem? Is this like the basis for something complex in mathematics? Or is this more like children's?
No, this is definitely like an analysis for probability and statistics, like that could be used in engineering situations. This is very much feels like a child's problem. Okay, so we try coding this up. That matrix is our Leslie matrix. The code is going to look almost exactly the same as the previous code, where you take your current value, you multiply it by your Leslie matrix to get your next time step. In this case, it's not a simulation time step. It's letting the probabilities play out based on the initial conditions and the probabilities that you're going to go one place to go. So before I do this, where do you think the person's going to end up? Like what? Actually, that's not the right question to ask. The right question to ask is, what do you think the probability is they end up at the bar? What do you think the probability is they end up at home?
Does it depend where they start?
They're exactly equal. I think it's 2/3. How can it be equal? We got 1/3 likelihood you're going this way.
If you look at the
2/3 likelihood you're going that way.
if you look at the odds, they're completely opposite.
You know, it's a little weighted. Right.
Yeah, except for 1/3 is.
So part of the answer depends on where you start. Right? So let's pick a starting location. Where are we going to start?
1 bar.
Okay. So for one exercise, let's start there. What would be your guess for the likelihood the person's going to end up? And how about over there? Okay. And then let's pick, this is another scenario. Okay? Where do you think the person's, what do you think the likelihood is they end up at home?
So it would be less. They would be more likely to end up at the bar if they started closer to the bar. And it wouldn't be 1/3, 2/3 if they started closer to home. Yeah.
I put those down.
Sorry.
No, I get worked up. Get worked up. You sure?
I don't know what the, I don't know.
So I'm asking
guess
for
probability.
spits in the dark because, shots in the dark because, like, you know, it's kind of cool to see what the simulation can do. So let's code this up real quick and then we'll take a break. You guys want the projector? Do you want the lights off or you guys okay? See, okay, we got the new projector, right? Okay. Let's look quick. So one thing that we have here is a matrix with a lot of zeros. I could type this whole matrix out, or I could do it more cleverly. What do you guys think I should do?
You should do 0.
Okay, so yeah. So I could start with zeros, right? So we'll call it probability matrix. I'm going to make it sized. So, okay, good. And just to be clear, let's verify that we get what I expect. I'm saying my size is 6, come out with p equals zeros in a matrix 6 by 6 zeros, right? You okay with that? So now what I want to do is put in my 1/3 and 2/3, right? Any suggestions on how I should do that? Yeah, you guys see a pattern? Well, let's say, okay, I'm going to do 4 something, right?
Yeah.
You guys are going to help me with that in a second.
It
And I
would
got
be
4.
index plus 1 for row for the 1/3, and then it would be
It's gonna be the row and then the index is plus 1 each time. No, wait a second, it jumps down. I don't know. Think about it.
So I've got some stuff here, which I don't know what it is. I've got some stuff here, which I don't know what it is. And I got some stuff here which I don't know what it is. Let's pick one. Which one do we want to work on first? The 1/3 or the 2/3? The 1/3. Okay. Where's the first index for the 1/3?
1, 2,
1, comma 2. Where's the next one?
2, 3,
2, 3.
3, 4. So
3,
it's
4.
plus 1 on both the row and the column each
plus
time.
1 on both row and column.
Okay. Can I use the same index to accomplish that?
Yeah, the 4 dot dot dot, do a plus 1 on both rows each time.
So I equals something colon something, right?
Yeah.
Well, before I do that, let's think about my 2/3 too. What's my 2/3 range look like?
3, 2, and then add 1 each time.
Right. So the easiest way to do this is just pick any range. It doesn't matter. And then adjust all the other indexes against that range, right? So help me pick a range. Like we could do, we have 4 values, right, for 1/3, 4 values for 2/3. So I need a range of 4 values. It almost doesn't matter what values I choose because I can adjust my indexes accordingly, right? So do you guys want to do 1 through 4, 0 through 4? Do you want to do 2 through 5? Okay, 2 through 5. Jeffrey tells us 2 through 5. All right, so then help me out. What are my indexes going to be for the 2/3 case? That's this one, right? If I is 2 the first time around,
You'd have I plus
2.
2.
I plus 1. All right, there we go. Okay.
I.
All right, great. And then this one. If I is 2 the first time around.
I minus 1?
Yep.
Oh, there's I, that's why.
And I.
I.
Yeah? Easy. Why did that one seem so hard?
Because we had to use our brain.
Right, and do you guys see what I mean by it doesn't matter what you choose for the range? You can pick 5 billion to 5 billion and 4. It doesn't matter. Just make sure your offsets are correct down here, right? So anytime you see a pattern like this, if it's zeros or ones or whatever, you can fill with zeros. Even if it's some unique number, but it repeats all the time, how could you do that? Like say if each of these zeros was actually 0.7. If all of those zeros was actually 0.7, I could just do something like this. Ones. Like, I don't want ones, I want 0.7, but guess what? 1 times 0.7 gives me that. So here I've got a big ass matrix full of all 0.7s. Okay? So you can use those, that ones and zeros, and which seemed almost like useless functions when we first talked about them. And you start to see now that they have some value. Okay, good. Good. So,
Question about the script.
yeah. I'm listening.
Could you show it?
Oh, yeah, sure. Let me get the font size back up.
So I understand why the left notation was I plus 1 and I minus 1 in those instances. Why was the right term just simply I?
Because it happened to match correctly to the 2, 5, right? The 2, 5. 1/3 starts at 2 and goes till 5, right? 1/3. Same with the 2/3. Remember, this is indexing. This is row. This is column. Yeah. Okay, so let's run this real quick. Make sure it looks right. Oops. That's pretty close, right?
We need the one.
Yeah, what are we missing? The ones, right? Where do our ones go? We have our special cases of ones. Where do they go? Up here and here, right? Okay, so what's that look like in my code? Just index it straight up. How do I get to that top left? Become a 1. Okay. And how about the bottom?
6.
Should I use 6?
And then
Ah, good. Nice call. right? It's okay to use 1 on the 1 because you know it's always going to be in that top left corner. But use the n for the other end because now if I suddenly have 8 intersections, I don't want to go back and change my code all up, right? What's that?
Can you do end to end or no?
Oh yeah, you could do that too. All right, so let's make sure this looks good. That look good? All right, so now we have to build my initial condition. Where do we want to start? Which intersection do we want to start? Let's do let's do intersection number 2. Yeah? So I'm going to represent that like this. 1, 2, 3, 4, 5, 6. Okay. And I'm going to be doing that math where I'm multiplying matrices, so this needs to be a column, right? We're okay with that still? All right. And now we actually do the math. And it looks exactly like we had before. No different. Let's do a display. T X. Suppress output, suppress output, suppress output. This is a theme for today. Cool. So this is the kind of situation, it's the kind of process where you're doing iterative math that you don't necessarily know when to stop, right? What do we call that? What kind of looping do we call that?
Indeterminate.
Indeterminate, right? So I put in T1 through 50. If you look here, from 41 on, it seems like it's all stabilized, right? And what is this telling us? Let's go back to the very, very top.
Let's go to the bar.
Yeah, like we're going to the bar.
What this is telling us is if I start here is where I'm starting, right?
Yep.
In that first step, 1/3 likelihood here, 2/3 likelihood here. Make sense, right?
Yep.
But in that next step, the probabilities start to shift a little bit. You see that? Because what it's doing is it's simulating through, okay, what is the likelihood you'll end up at this square in the next step? Yeah?
So that step 2, like, did that step actually?
It did the probability of the step. So in step 2, you have a 0.3%, 0.3 likelihood that you're here, a 0.2 likelihood that you're here, and a 0.4 likelihood that you're here. In the third time step, these are the probabilities that you'll be in any of those spots. And so it starts to settle out pretty quick. There. By step 37, I think we're settled, right? Once you have no likelihood of being in the middle, it's done. So that could be your conditional, right? You could set this thing to repeat as a while loop, or you could set this thing to repeat like 1 million times, but have a conditional check in there to see, hey, when does the problem stabilize? We saw here and talked about this problem enough that we know that if there are no likelihoods that you're in the middle, you're done, right? Because that means you're either there or over there, and by that definition of, we're not going away. Once we're at the bar or the home, we're done. So this was the case of starting at intersection 1. And the likelihoods that you end up at home is 0.4839. And the likelihood that you end up at the bar is 0.5. So just a little bit high on the bar, but not a lot, right? So let's try another starting condition. Which was the other one? Like this one, right? What do you think will come out of that?
That'll be a lot higher at the bar.
I would think so, yeah? Yeah.
Like those others.
So given the same, the preference to go 1/3 that way, 2/3 this way, if you start out here, the likelihood that you're going to end up here is pretty good. Way higher than that 2/3 you might sort of intuitively think without thinking through the iterations. So shall we try something interesting? Let's see. Let's start here, right? There's no midpoint because we have 6. So let's see what does it look like at that spot. Not too bad. Still end up at the bar.
I think the first one is the most interesting.
So let me ask you a couple of questions. How could I, in terms of like making dynamic code, making code that's flexible for this, how could I adjust this code a little bit to make it work for a lot more circumstances?
Well, if you have more intersections, you have to change your for loop.
Yeah.
Maybe n-1 instead of 5.
Okay. Great. So now that takes care of if this thing grows because I've got more intersections, right? This takes care of that. Does everyone see that?
Yeah.
Yeah. Does the 2 need to change? No. The 2 stays the same, but what changes is where the bottom of this as this matrix grows out that way, where the bottom of it is. Good. What else did I change?
Than your 1/3 because your probability.
Yeah, my probabilities. Okay, good. So let's call that home tendency. Let's call it P home. Home and P bar. Why did I do that? Okay. What else? Anything else here I can change? The minor one.
I was thinking like you could, it would be maybe bigger, but you would have, like intersection 1, intersection 2, intersection 3, and then those would be your variables for inside your X.
I'm not following. Tell me.
Well, I mean, you like label your intersection.
Oh,
so
X intersection equals 1. So you can just change it up there with a number.
But you were getting at something else.
There you go. There you go.
You're getting at, were you getting at the same thing or something else?
Yeah, the same thing, but like
Okay.
the long way to do it.
And then, of course, I think the other big thing you could do here is that conditional, right? You could make this 10,000 while so the conditional math is going to be tricky. So I'm going to make, well, sometimes we'll call this a flag or a Boolean to tell us to keep going or not, right? So if keep going is equal to 1, oh, sorry, this, you need to tell me. Okay. So if keep going is equal to 1, what happens with this while loop? It just keeps going, right? And I described what my stopping conditions might be. Does everybody remember what those were?
I'm sure it was.
If everything in the middle is 0,
Yeah,
right?
yeah. How might I check for that?
Wouldn't you have to index
Yeah,
through it?
the index numbers of the 2 that we kind of.
That would be one way to do it. Can I think of another trickier way, like sort of more crafty? Right, so here's X. And what I want to do is check that these are all 0, right?
You go like.
What's one way?
2,
I could sum them all. So I could take all of these and I could sum them. Help me out. Give me some more. What else do I do?
While they're not equal.
So I can do sum of X, right? But how do I specify only that range?
2 and then colon. Well, actually, no, 2 colon 5.
2 colon n minus 1.
And minus 1.
Yeah.
What do you guys think about that? Super easy way. I don't have to like index. I don't have to do 5 conditionals for every one, right? I just say, well, I know I want all 0s here. I could sum. How do I get the right indexes? Well, I'm going to start at 2, and I need to go all the way to the last one, but one before it, right? Yeah. Yeah. Okay, let's try it. sum of x 2 colon n minus 1. Yeah? What do I do?
You change, keep going.
If that works? Whoa. Start in section. Not sure what in section means. Does anybody know?
Procedure.
Oh, what did I do wrong? Oh. There's a problem here. If I want to keep progression of time,
Correct.
if I want to keep, because I've lost, remember the 4 t equals 1 through some number? That was giving me my time steps. Now that I have a while loop, I no longer have those time steps. How can I fix that? I can just make it up. And what do I do every loop? Right. So where should I start t? Let's start t at t equals 1. And at the end, I can go t equals 1. Yeah? Let's try that again.
Well, you're already going to display t, so you can just suppress that last one.
Oh, yeah, thank you. My numbers don't look as good.
And it's doing the e to the 3 every time.
Yeah, where's it doing now? Oh. Nope. We didn't have that last time, did we?
Mm-mm.
Okay, so.
But that's like what I was talking about, where it was making this decision to change the format on its own.
So it's because of t changing.
U and A.
There we go.
Oh,
Not like that. What did I do around here? That's an easy way of doing this. Why is
Let's go to the bar. Every 10.
oh, there's some initialization problem happening here. Dang. No?
Now you're missing the colon.
What am I missing from?
Display.
Oh.
No, he's concatenating as he wants them to be like side by side.
Oh, I know what's happening.
Your magnitude is just off.
No, I know what's happening. Okay.
This is not reaching 0.
So because I'm asking for this, before what we were seeing, we visually thought the number was fully settled out. We saw zeros here, right? But the reality was at decimal place 10, it wasn't 0. And so now that we're demanding 0, we're actually getting to time step 2,752.
Wow. Well, that's 10 to the 3rd, though.
Yeah, he already made up as in 2000.
Yeah, right? 2,752.
That's what I'm talking
Yeah. And that may actually not really be 0. That's just based on the precision of the calculations that we're at that we're getting to 0.
But also, it's just like in the other math, there could just be rounding stuff happening.
Yeah. So what might be a better way than insisting on getting to 0?
0.1.
Pick some small number. Yeah. So let's do that. Yeah. I'm gonna go 0, 1. There we go. That's still too big though. See that? That didn't actually get us all the way to our solution.
About like 0.0001. There we go.
Now the key, like for any problem like this, especially when you get into engineering work, it's like what is the precision that's important to what you're doing, and basing that threshold on that precision. Cool. Okay, that took way longer than I was expecting. Now you guys deserve a break. Or questions, either way. It's a break or questions, your call. But here's the code. If anybody has a question, come ask. Let's take a break for sure.
Did you see how he created like those formulas? He just was using it. Like he did like 5, 1 to 25, and then all that just moved through that time. But the stuff inside the loop we saw was quite a lot. Yeah, that was an example. I was trying to think of one earlier. I don't know what you do that. Yeah.
Professor?
Yes, sir.
You're not science, it's like a midterm report.
Oh, yeah.
What is it?
I don't remember. I never did.
It's on campus.
Nice fire area. Eat it your own way.